Now we want to practice finding a basis for an eigenspace. So here's a 3 by 3 matrix A, and suppose we're told that -2 is an eigenvalue for this matrix A. And we're asked to find a basis for the collection of all eigenvectors of this matrix A corresponding to the eigenvalue -2. So I purposely wrote this out long ways, but we have a term for this. The collection of all eigenvectors of A corresponding to a particular eigenvalue is called the eigenspace, for in this case lambda equals -2. And there's some specific notation for that. This E with the subscript -2 refers to the eigenspace corresponding to the eigenvalue -2. All right, so we're solving for the eigenvectors. So that means we're solving for the vectors x in the equation ax equals the specific multiple -2 for this eigenvalue times x. We want to find all vectors x, where when we multiply a times x, what we get is just a scalar multiple of x, right? That's what it means to be an eigenvector. You multiply it times a matrix, the vector doesn't change direction, only length. And in this case, the specific change in length is, well, -2, opposite direction, double the length. The specific multiple, I should have said, is -2. Now, I've shown in the notes that this is equivalent then. We could take this equation and express it as, so suppose you move the 2x over here, so we could write this as ax plus 2x equals 0. And we could express that as a plus 2I times x, where I is the 3 by 3 identity matrix equals 0. In other words, something else I've said in the notes, the eigenspace for -2, so this E -2, is equal to the null space of the matrix A minus the eigenvalue times I. So in this case, the E -2 is equal to the null space of the matrix A plus 2I. It's plus because it's the minus the negative. Minus the -2 times I. Which is also what I'm saying here. So we want to solve for the vector x in this equation. Which means we want to solve for the vector x in this equation, so we want to find the null space of this matrix right here, A plus 2I. Okay, so then what we need to do is form this matrix A plus 2I. So here's your matrix A. Make sure I copy it correctly. Oops, 1, -3, 0, 4, -13, 1. Okay. Plus 2 times the identity matrix, the 3 by 3 identity matrix, I should say, which is this. Okay, so if you say you multiply everything in here times 2, you're going to end up with 2's along the diagonal, and then you add those matrices together, you're going to have 1 plus 2, and then 0 plus 0, -1 plus 0, 1 plus 0 here, -3 plus 2, 0 plus 0, 4 plus 0, -13 plus 0, and 1 plus 2. Again, I'm saying 2 when I point to this because it's the 2 times the 1. When you distribute this 2, you'll have 2's here, and everything else will still be 0 when you multiply times 2. And so you end up adding 2 just along the main diagonal there, and then every other entry, notice, stayed the same. All right, we want to find the null space for that matrix. So this is 3, 0, -1, 1, -1, 0, 4, -13, 3. All right, so if I'm row reducing this, I don't really want to introduce thirds if I don't have to, so I would probably do a swap row 1 and row 2. So I'm trying to get this in echelon form, if not reduced echelon form. So I'm swapping these rows first. And then now I want to zero out these entries, so I'm going to do -3 row 1 plus row 2 and -4 row 1 plus row 3. All right, let's see what we get here. -3 plus 3. This will be +3 plus 0. 0 plus -1. -4 plus 4. 4 plus this. And 0 plus 3. Okay. We can make this a 1. We don't absolutely have to. Remember what the real mission is, to solve this system where we've got AX equals 0. I do need to zero out this entry here. I'm going to focus on that because I can do that fairly easily if I do 3 times row 2 plus row 3. So 3 times row 2 plus row 3. Make that the new row 3. See if I can get to something usable here. So 0 plus 0, 9 plus -9, and 3 times this would be -3 plus 3, so 0. Which, by the way, you're going to have to end up with a free variable when you do this. Because eigenvectors are, by definition, non-zero vectors where AX equals lambda x. Your solution here can't be just the 0 vector. And if you get a pivot in every column, your solution is only your solution set is just the trivial solution, the 0 vector. So eigenvectors have to be non-trivial solutions, which means you're going to have a free variable when you reduce this. So that's just a way to catch yourself if you've made a mistake and you end up with only the trivial solution, then you know something's gone wrong. Okay, so we want to describe this solution set. I suppose it's up to you guys how you would deal with this at this point. You could convert back to a system of equations and then solve from there. I guess I'm going to continue to reduce to the reduced echelon form. So I could do 1/3 times row 2 here. Make that the new row 2. I'm going to be in the corner of the board. I know this isn't ideal here, but so that'll be -1/3 and then zeros here, and then all zeros on the bottom. And then I want to if I want to get this to the reduced echelon form, then I want to zero out that entry. And so one last row operation, I'm going to bring it back up here. I guess we don't need any of this. So if from that point down there, if I do row 2 plus row 1 and put that in row 1, then I'll have the reduced form here. So we have zeros across the bottom. And then we'll have 0 plus 1, 1 plus -1, -1/3 plus 0, and then 0 here. Okay. So our solution set looks like this. These are our coefficients for x1, x2, x3. So x1, in fact, let me write this over here. 1x1 minus 1/3 x3 equals 0. So x1 is equal to 1/3 x3. And then 0x1 plus 1x2 minus 1/3 x3 equals 0. So x2 equals 1/3 x3. And x3 is a free variable because it can be whatever it wants to be. So our solution set here, our vectors x are equal to, so x1 is 1/3 x3. x2 is 1/3 x3, and x3 is a free variable, x3 equals x3. So one basis that you could give for this eigenspace, E-2, would be 1/3, 1/3, 1. x3 can be any number. So every solution, x, so every vector in this eigenspace is going to be some number times 1/3, 1/3, 1. This would be a perfectly acceptable basis. This is going to have dimension 1. We just need one vector as the basis. This works. Or what you'll see sometimes when you check answers, say in the back of the book, a lot of times they like to make the entries in your basis vector integers, so nice whole numbers, which you can do because x3 here can be any number, and we could set up a parameter that's also equal to any number. You can do something like let x3 here, let's look at this form, equal 3t, where t is any number. We're just introducing this parameter t. So if we insert 3t in for each of these x3s, 3t, 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 then you end up with just t, here, that's going to lead you to 1/3 times 3t, so that's just t. 1/3 times 3t, so that's just t. And then 3t here. So this is t times the vector 1, 1, 3. Which notice 1, 1, 3, that's just a multiple. That's 3 times this basis vector. Because when we say that 1/3, 1/3, 1 is a basis for this eigenspace, we're saying that the eigenspace consists of all multiples of that vector. Well, so if you use any other scalar multiple of this vector, that would work. That's going to give you an equivalent, that'll generate an equivalent set. So you could, as your basis vector, and any time you have fractions here, if you want to multiply everything by your least common denominator, in this case 3, and that gives you 1, 1, 3, that will yield an equivalent basis. So either of these answers would be acceptable.